Now, our ultimate aim is to get a good handle on the standard model, which is a theory that incorporates the known interactions except gravity into a gauge theoretic framework, okay, where gauge invariance is playing an important role. The Fermi theory was developed earlier before we realized the importance of gauge interactions, and is an approximate theory. It's an approximation to the true gauge interaction theory of weak interactions. But it works very well at low energies, below say 100 GeV. Okay. So we will study, because that was how people found out about weak interactions. And then as we move further into the course, this will be absorbed into the full gauge theoretic framework, which studies QED, QCD and the weak interactions. Okay. So we are not going to approach this from a gauge theoretic viewpoint, but we are going to approach it from an empirical viewpoint, where there were things happening in experiment and the theory was built in a certain way, step by step, with Fermi playing a key role in that. So this is a new kind of interaction. QED was well understood, and it was known that there are strong interactions between neutrons and protons and so on. And this was a third type of interaction that people learned about looking at experiment. Now, other than being an approximation that works, this is important from another point of view. That is that without having a framework, underlying gauge theoretic framework, how do you construct the interaction Lagrangian for a new interaction? Okay, that's very valuable, because today, in spite of having the gauge theoretic framework, we are at a situation where we want to go beyond the standard model, which is working very well. There are some anomalies, there are things that you don't understand. In most of them, it is unclear whether it's the experiment that is wrong or there is some new physics. So when you want to build or go beyond an existing framework, that as a practical matter, what does that mean? Well, you add the new interaction you have in mind to the existing Lagrangian. Okay, so L standard model plus L something. So how do you build these? By looking at experiment. You don't know otherwise. So if you're doing the kind of physics that looks closely at experiments and tries to understand the next step, then this is how you will proceed, the way Fermi and others proceeded for the weak interaction. So this is also important from the point of view of how do you construct an additional interaction term. So you have QED, you understand much of it. How do you use it to construct this kind of interaction? Okay, so that is just by way of introduction. So why was this kind of, how was this kind of interaction, how did you start realizing that there's something here? So it started with nuclear decays. Okay, so essentially people saw that if you had a nucleus of charge Z, which means Z protons and A nucleons, okay, they observed that there were decays which this antineutrino was not observed, and it was again Pauli and others who realized that to maintain energy conservation and angular momentum conservation you needed this. That's a different story, so I am not getting into that now. But they observed decays like this, in which they could see the electron, and then they had a leftover nucleus. And then there was this other particle which neutrinos are very difficult to observe. So we'll see that later on in the course. But this was the kind of decay that was being observed. So the underlying decay here is N goes to P, the proton, plus E minus plus nu E bar. So it's happening inside the nucleus. The neutron decay was being observed. Now free neutrons also decay, and tau for the neutron when it is free was something like 887 seconds or something like that. Okay, the lifetime of a free neutron was this. These are bound neutrons. So lifetimes of the light nuclei were closer to this than for the heavy nuclei. So you have a neutron that's surrounded by a cloud of strongly interacting particles. This is a weak interaction. I'll explain why. But this is a different interaction. So most of the time the strong interaction is overwhelming of this weak new process. Okay, so inside this is what is happening. So if for instance I look at some lifetimes, hydrogen 3 goes to helium 3 plus E minus plus nu E bar, and that lifetime was observed to be 5.6 times 10 to the 8 seconds. So you see already it's living longer than the free neutron, okay, when it's inside. But what is happening is basically the same process. So there's also 14 carbon going to 14 nitrogen plus E minus plus nu E bar, and that lifetime was 1.8 times 10 to the 11 seconds. So there's a large difference in the lifetimes that are being observed. These lifetimes are large. So what does that mean? That means the interaction that is causing this is very weak. Otherwise it would happen very fast. Okay. So for instance, strong decays happen very quickly. You don't have to wait this long. This means you are waiting if the nucleus is at rest or the neutron inside is at rest, which it never is. Okay, there's always this Fermi motion inside. But okay, practically at rest or on the average at rest, then you're waiting. If it's free, you're waiting this time. If it's trapped, you're waiting depending on what the nucleus is. So it's taking a long time, which means this is not the strong interaction. Also, you have some idea of how much an electromagnetic interaction, how quickly an electromagnetic decay should happen. So this is much longer than that. So the conclusion is that the strength of that in this new interaction is very weak compared to electromagnetic and strong. Okay. So these are all observations, and they signal the fact that there's a new interaction that we have to worry about. how do we build its Lagrangian? So this, you are familiar with carbon dating? Okay. So this is basically what is used for carbon dating. So you have these neutrons hitting the upper atmosphere from cosmic rays, and they hit this, and N14 plus a neutron will give you carbon 14, which is an isotope, and decays in something like 8,000 years. So the carbon 12 that is already there in the atmosphere, okay, which is made up of this carbon dioxide, which essentially has the carbon atoms in it. So some of the nitrogen is being converted to C14, which has this half-life. Okay, let me explain. I suppose you know that half-life. Usually for nuclei they quote half-life, so I'm just it's tau times the log of is called half-life. Okay, so there is a half-life involved here for C14. So what happens is that the carbon in the air and the atmosphere is being absorbed by the trees or the plants, and those plants are being eaten by us. So we are taking in this ratio of C14 to C12, which is being decided by the bombardment of neutrons in the upper atmosphere. So those rates are known. So you know how much C14 there should be for every C12 atom, sort of. Okay. You have some idea. So when the organism dies, the plant dies, the animal dies, then this ratio is sitting there in their bodies because they were eating all these plants which had this ratio, and then the C14 starts to decay. And depending on that ratio, you know what it was when it was alive, because then it's in equilibrium with the rest of the atmosphere. Then it dies, so it stops eating it. So this C14 decay then allows you to see now how much of it is left. So knowing the half-life, you can compute that when did this, how long ago did this organism die, or in other words, how long ago was it living. Okay. So this has this very important carbon dating application. I'm just mentioning it for you. So there are also decays. Were observed. So this the underlying decay here is that you have one less positive charge left. So your proton has decayed to a neutron. A is the same, and then you have to balance the positive charge you have this E plus, and to balance electron number you have this. Is this clear? This cannot happen for a free proton, because this has a mass which is lower than the mass of the neutron by a slight amount. Okay. But when you are inside a nucleus, there's a lot of other dynamics going on. So you draw on that energy to allow this to happen. So as far as we know from experiment, the proton is absolutely stable. It does not decay. So why would the proton not decay to some lighter mass particle like pions? So that's another conservation law that is observed. That's the conservation of baryon number. So these baryons are apparently carrying a charge, and it seems like that charge is conserved in all the interactions that you see. But you see, you have to distinguish between a charge that is associated with a gauge theory and a gauge interaction, and a charge that is conserved for some reason other than that. Okay. So for instance, baryon number is a charge which does not have a gauge boson or a gauge theory associated with it. That's not like electric charge. The electric charge has a gauge theory associated using the another theorem with the conservation of electric charge. Okay, so then there's a gauge theoretic framework there. For baryon number or for lepton number, there are no associated gauge bosons and there's no associated gauge theory. These are what are known as global symmetries of the model. As you have learnt in your field theory that there is a local symmetry associated with, say, QED. Okay, so this is the difference. But there are conserved quantities like this, and baryon number is supposedly one. So then what do? You look for proton decay. See, because we know that gauge charges are really, really conserved. There's no good reason why it should be, or at least no good reason that we have come up with, why it should be conserved. But it's conserved. And there have been experiments that have now tested proton lifetimes to be greater than, I forget the exact number, but it's like 10 to the 33 seconds. So that's a very long time. The age of the universe is something like 10 to the 17 seconds. Okay, so the proton is stable to a very high degree. Why is it stable without having this kind of local conservation law associated with it? We don't know. Okay, so these are among the questions that we don't understand. But when a symmetry is usually not supported by a gauge interaction, you put a lot of effort trying to see if it is indeed broken. And that's the same with proton decay. Okay. So, can you guess how you get to, are you really waiting for 10 to the 33 seconds to measure this? How do you do this? How do you arrive at this? How would you come to this conclusion that obviously you are not waiting this long for it to decay? So the thing is, if you have a huge number of protons, say in a water tank, then at least one of them will decay. Supposing I have 10 to the 33 protons, there is a lot of protons. We don't have tanks that experiments that big. But if you have a large number of protons, then one of them might decay in a year, or in 2 years, or in 3 years. Okay. So based on how many decays you would have seen had the lifetime been this, because the entire tank will not decay once the clock hits 10 to the 33 years. Okay, so you get the idea. It's a distribution. So that allows us to put this kind of okay. here's at a more basic level, say non-nuclear level. Here's an example. Weak interaction or weak decay. Is pion decay. Pi plus minus goes to muon plus minus plus the neutrino. So if it's mu plus, you will get a new mu, otherwise you will get a new mu bar. Because lepton number is being conserved. Remember, lepton number is another one of these accidental symmetries that we don't completely understand why they are conserved. Is this clear? Okay. So this lifetime for the pion is let's see how much is 2.6 times 10 to the minus 8 seconds. It's the same kind of decay, weak decay. Very different lifetimes depending on whether you're looking at some heavy nucleus or whether you're looking at a pion. It's still much larger than what would happen in case of an electromagnetic or a strong decay. But there is a, so for a pion, for instance, with velocity beta, the decay probability, so P decay is going to be e to the, so the way I've written it is e to the minus L over 7.8 1 minus beta square over beta. So what is this 7.8? The 7.8 is how much it would travel meters. So P decay or P decay in length L, I should say. The probability that it will decay in length L. 7.8 is C times tau. Okay. So I multiply the rest lifetime by this to get a distance. So this, you're looking at it in the lab, it's moving with velocity beta. This is the general decay formula that you will use to find what is the probability that it will decay in length L. Is this clear? See, this part is simply something moving with velocity L. Now I want to know how many will decay in 100 meters. So then I'll put L here and get the answer that way, knowing how fast it is traveling. So these are things that I'm sure you're familiar with, but just reviewing them.
How can we know that that this only seeing this tau we will decide that this is a weak decay or strong decay?
So as I said, from a lot of data, they know typical lifetimes were the pi to decay electromagnetically. There's another issue here. Neutrinos don't couple to photons, okay? So it can't be electromagnetic. Neutrinos don't couple to quarks or gluons or strong forces. So it can't be electromagnetic. So this was the first, so that's probably the main indicator. Because as you see, the lifetimes are varying a lot. So you need a lot of data before you can draw conclusions based on lifetime measurements, that this is the same interaction here and here, because there is 16 order magnitude difference. But a quicker way of recognizing was that, well, it can't be electromagnetic because this is not carrying a charge. So, and it can't be strong either because this doesn't couple to strong. So it's a new interaction from that point of view. And in fact, when seeing these decays, they had to postulate the neutrino to, as I mentioned earlier, to get energy conservation and spin conservation. So then they realized they were dealing with a new interaction, because prior to that they didn't need neutrinos. They had a new particle that was there and it only seemed to have this new interaction. Okay, so all of this was happening, which eventually gave birth to the idea of a neutrino. And that was different from, say, discovering an electron, because the neutrino basically does nothing. It has an interaction mean free path length of light years, so it's very hard to get it to interact, and it's not carrying charge, and it has very little mass. So you just don't see anything. All it does is have missing energy. So you had to use energy conservation to deduce the fact that there is an object here. Okay. Is this clear? So in today's lecture there are more words than writing. We'll get back to calculating the muon decay amplitude square maybe in the next lecture. But today's lecture is more about trying to understand what the weak interaction is about. Okay, so there was something which was a bit strange about the pion decay as it was observed. So what they observed was pi minus to mu minus mu bar, or pi plus mu plus mu. And then sometimes they observed, say, pi minus to E minus plus mu E bar, also decay to an electron. So from what we learned earlier in the course, you know that when you decay to light particles, you have a phase space advantage. So particles prefer to decay to light particles because the heavy particle carries away more energy, and you have this factor of 1/2 EI and so on. However, it was observed here that decay kinematics is not being followed, and this is preferentially by far decaying always to muons. So that was not understood. We will understand it a little bit later in the course. But the observation is that branching ratio for this. Remember, branching ratio is the decay width of this mode divided by the total decay width. So branching ratio for this was found to be 0.99988, and the rest of the time it decayed to this. So that again is something that had to be understood, and we'll come to this later, but this is not what you expect. Okay. So this again I want to emphasize, of course that reflects my own personal biases about how you do physics, but I want to emphasize the importance of experimental observation in understanding something. Okay, your naive theoretical calculation tells you that it should decay to the lighter states. It doesn't, and the discrepancy is huge. So that is telling you that you are going to understand something new here. And without that knowledge, I mean, how do you sit and deduce that this will happen? You can't. You have to look at what is being told to you by nature or by experiment. Okay. So we will return to this. But now we want to understand the Fermi theory a little better. So I'm going to look at muon decay, which is a good example to study. So it was observed that the muon decays to E minus nu E bar nu mu, and the lifetime was 2.2 10 to the minus 6 seconds. Okay. In GeV this is 3 times 10 to the minus 19 GeV. Okay. Seconds has the same unit as energy, but delta E delta T equals h bar, which is 1. So
inverse of energy.
what's that?
Second is the energy. So inverse of energy.
Yes.
Delta E.
Yes, because this is time. Okay, so C tau, for instance, for this is 659 meters in vacuum, and is many meters in ordinary matter, because the muon doesn't interact strongly with the protons and nucleons as it passes through matter. Okay. So it will decay after a while because there is this decay mode, but it still will travel a long time before it decays. So the muon is a very is a relatively simple particle to detect. Okay, so people prefer channels or modes which are contain a muon, because then they can identify that this is happening better. Okay, so the muon is a good particle that doesn't decay very quickly. What about the electron? Well, the electron in matter bremsstrahlungs a lot. So it starts throwing out photons at a rate much higher than the muon. So when it does that, these photons again in matter become E plus E minus pairs. So the signal becomes very diffuse, as opposed to a muon, which is a clean signal, does not bremsstrahlung as rapidly as the photon. Okay, so by this time it was realized that you are dealing with a new interaction, and that you have to learn to build the interaction Lagrangian for this new thing. So from QED you had learned that, well, I have these new U's and V's for Dirac spinners. So these are all Dirac particles. So I can use that to build the new interaction. Okay. So the question was, what is L int for the weak interaction? and you do it by observing things. So you are observing these decays. So you can write down possible forms. Okay. So L int, for instance, could be, say one possibility would be, you look at these particles which are there, and then you say nu mu bar, then something, and then mu, and E bar, then something nu E. Okay, so these some combination Dirac gamma matrices. Okay, you're following the kind of thing that happened in QED which you understand. But there was gamma mu. It doesn't mean that every interaction will be built from just gamma. So you don't know, okay, until you again go and check it out against experimental data. But you know that, okay, Dirac spinors are represented by U and V objects, and initial state is particle is U, final state particle is V, so on and so forth. Although that you know from the Dirac equation. And here you have to put in some gamma matrix, like you did in, or combination of gamma matrices, like you did in QED. So there's one possibility here. There's another possibility that you can write down. So you could have the two neutrinos connected to each other times E minus connected to mu minus.
One thing, sir.
Uh-huh.
Weak interaction is only valid for decay process. I mean, is there any scattering process where we can
Yes, no, there are scatterings. Today we are talking about this because we just studied decays, 2 and 3 body. So we are going to look at examples, but more importantly, historically, you didn't have energies to get cross sections large enough for the weak interaction. So weak interaction cross sections in some cases involving the neutrino grow with energy up to a certain point. So you had to go to high energy to see scattering processes. But there will be scattering processes like nu mu, say mu minus, and then this is the weak gauge goes on, which we are not looking at right now. We are doing an approximation to the full gauge theory. But this will happen. Say proton, okay. Proton, let's see. This is carrying away positive charge. For charge to be conserved this at this vertex. So it's coming here and hitting, so let's say you have a neutron sitting in the matter nucleus and it gives you a proton. Okay, so there is a scattering, weak scattering process. Okay. So there are processes which we will study. Okay, but because here the aim today in this lecture is somewhat different, I am looking at weak decays. This will come.
in all type of weak decays, antineutrino is involved. I mean, neutrino antineutrino is involved in all cases of weak decay.
Yes and no. Almost all the decays I can think of, you have a neutrino or antineutrino.
Which gauge group describes this interaction?
So you have in the standard model you have SU3 for strong interactions, okay, color. Then you have SU2 left. This is something we'll study part of it today. The left-handed gauge group. This is for the weak part. And then you have what is called U1Y. This is called hypercharge. And things get complicated. There is some symmetry breaking. We will study that. And in the end, you are left with SU3 and electromagnetism once there is symmetry breaking in this group. So all that will come. But to answer your question briefly, the weak interaction has a SU2L group structure, where things couple only to the left-handed polarization of the fermion. Okay, so none of this was known at the time these observations were being made. So they started with a simple diagram like U minus, that's the muon decay, and then this is happening. E minus, nu E bar, say, and nu. It is on the basis of this simple diagram. So there is a contact interaction. What is missing here? It's the gauge boson that is transferring the force, which is missing. Because as I mentioned, the gauge theoretic structure was not understood. So they're just putting it as a contact interaction. Okay. So based on this simple diagram, I am writing this. Okay, you see that either mu, this is one possible current, which in a more gauge theoretic framework would be something like then there's a gauge boson, okay, and then you have electron and so some kind of current you would build here involving a gauge boson, okay, for a given weak interaction. So based on that I am writing down a current interaction, okay. So this is being done because in QED you saw that there is a current interaction, okay. For instance, you have E minus gamma, say mu minus current, which has two fermions, some gamma matrix at IE gamma mu here, another current, and contracted to give a matrix element. Okay, that was, so they are using this structure based on that kind of thinking. Any question so far?
In this air interaction, we could have more possibility.
We could, yes. But of course, when you are observing things and trying to build, you move one at a time and then add things as you understand them. So, if I am trying to understand this, then these are the possibilities that I can think of. Okay. If you are trying to understand full weak interactions, then of course you have to be more careful when you draw the full L interaction. But this is more of a step-by-step phenomenological approach looking at experiment.
What is the electric charge of electron neutrino here?
So
Electric
the neutrino is chargeless.
So how can we say this is a current because there is a current interaction, that's fine, but in this case electron, some combination of gamma matrices and anti-neutrino. So
Yeah.
how can we get some?
Right. Remember the diagram I just drew. Okay, this has to carry away some charge. So you are dealing with a charged gauge boson. But they were not thinking like that. They didn't know these are very heavy gauge bosons. They were discovered later. And when it was realized that you have to build the interaction using gauge symmetries. Here they're just sort of trying to understand how to write down a Lorentz invariant matrix element that accurately gives them the decay rate that they observe. Right? So you are trying to just match experiment because you don't know enough. It's like the situation we are in now. We understand the standard model very well. They understood QED very well. Okay? And then they see something new, they don't know how to do it, and then they're starting to add little things that might be correct or mostly things are wrong. You learn that as you do physics, that mostly your ideas don't work. Okay, and you're lucky if you have one really good idea in your life, you're really lucky. So, and what is a good idea? Well, there are many people come up with many good ideas because there are a lot of bright people in this field. But a good idea is defined not as something very smart or put forward by a very intelligent person. A good idea is something that nature also agrees with. An experiment tells you that, yeah, look, this is what you observe. So good is defined somewhat differently in physics. So you will find examples of extremely brilliant and bright physicists who know huge amounts of physics. But okay, well, they've had many brilliant ideas. They've written papers which have taught other people a lot. But unless you predict something that people go look for and find, like supersymmetry, this is what has happened, as I've told you earlier also. So you don't find it, or you haven't found it so far, although you expected to find it very quickly once the LHC was done. So again, that's maybe a brilliant idea, but from the physics viewpoint, it has not yielded the kinds of results that you want. Because nature, perhaps, you may still find it, I don't know, but nature perhaps has not chosen that kind of path. Okay, so when you're doing this kind of thing, then there was another experimental observation that you have to worry about. And that was the fact that they were finding that family lepton number is conserved in interactions. Okay, so what does that mean? So the reason I'm talking about that is that based on that, you will be able to discard one of these possibilities and work with only one of them. Okay, so they had seen that LE, the electron family lepton number, which was +1 for E minus nu E and -1 for E plus nu E bar and 0 for everything else. Okay, and the same for L mu, L tau. So this had a muon lepton number. this had a tau lepton number, and these were the values. Particles were +1. You can assign it randomly as long as you're consistent. So particles had +1, antiparticles -1, and this was observed to be conserved. How do you know that? Okay, so you know that because so family lepton number observed to be conserved. One of the reasons, for instance, mu minus 2e minus gamma, otherwise would have been observed. Okay, this is violating this muon lepton number of +1 on this side, 0 on this side. There's electron lepton number of +1 on this side and 0 on this side. So both are being violated in some. Okay. So this is not seen. There is an electromagnetic decay. Why? Because it involves the photon. Okay. So there is some charge interaction involved. So here they measured these branching ratios. Okay, they found that this is less than 5.7 times 10 to the minus 30. Okay, because the muon dominantly decayed, as I already said, to nu mu plus E minus plus nu E bar. This was the dominant mode. The branching ratio for this was observed to be much smaller. This is electromagnetic. If it were really possible, this would have a much faster decay rate, because that coupling is not weak. This coupling is weak. Okay. So, but this is what was happening. So for instance, they saw that family lepton number somehow is conserved in the decays that we can see. Okay. So they wanted to respect that when they were building this. So you can see something like this kind of current will violate family lepton number at the vertex. Okay. So things are conserved not just overall, but also at the vertex, at every interaction vertex. So then you will not build your Lagrangian with this, you will build it with this. But you still don't know what these things happen. Okay.
So your branching ratio is a not zero for this case, so there are some probability to get this type of electron number violating process, like muon to electron.
Yeah. Okay. So that's a good question. See, the statement is that it is less than this, which means if it were this much or greater, I would have seen it in my experiment. So it's limited by the capabilities of your experiment, what kind of bound you put. Now a better experiment, so this is minus 13, a better experiment which comes along in 10 years would put minus 14 or minus 15 if they don't see it. So this is decided. So until you see it, you can never say that it's zero, unless it's dictated by some symmetry that you really trust. So as I said, this kind of conservation is not related to a gauge symmetry or a local symmetry. So you're always thinking maybe it's broken. Okay. And so you're looking for that breaking. I mean, people also look for charge conservation violation. But those searches are perhaps not where you expect to find a violation. Here you might, because there's no underlying gauge symmetry. Okay. So see, baryon number, as I said, for instance, is like this. It's also conserved. You find that protons don't decay. The proton is the lightest mass baryon. So if you're trying to build a theory beyond the standard model, and then you find that there is this accidental conservation. Accidental meaning there's no good reason for it. It's just there. You observationally you see it's not decaying. So you would try to, if you're trying to build a theory beyond the standard model, one of the things that you would keep in mind is that, look, the standard model already has this conservation law. It's already being respected by experiment to a large extent. Maybe it's associated with a gauge symmetry, but I'm not able to see that because those interactions might be very weak, because I have to go to very high energies to observe those. So then one of the things that you would try to add as an extension to the standard model would be an actual gauge symmetry respecting baryon number. Okay. Now, when you do that, there are other problems that you find which have to do with something called anomaly cancellation and so on. So you have to add more particles to your theory. But in general, these symmetries like family lepton number, total lepton number, baryon number are being respected to a very high degree. Family lepton number is actually broken, I will come to that, by neutrino oscillations, but we will, you can't see those effects in 1 to 2 scattering or something like that, because they're very small. So when you see these symmetries being respected, you are naturally led to consider first, when you want to extend the standard model, gauge groups associated with symmetries that are already observed, or conservation laws that are already observed, like lepton number, baryon number. Okay. So those are attempts, but they run into various kinds of difficulties, which is part of the difficulty of going beyond the standard model in a good way. It's a very real problem. It's a problem that has not really been solved yet. There are a lot of issues, a lot of experimental constraints that prevent you from choosing this gauge group or that gauge group. And so it's a complicated business. Otherwise we would have theoretically just written down the next Lagrangian term. But we have not been able to do that because there are many, the standard model just works so well that every time you add something new, some standard model measurement somewhere would have received a small contribution from this new process. But it didn't, because you measured it more accurately, very accurately there. So you can't have this interaction. So there's a huge number of such constraints that make an extension of the standard model difficult. So in that sense, experiment can only put a greater this kind of limit. It cannot say that, unless you measure the decay, then you can say that the branching ratio is exactly this. So in general, I have come to the conclusion that building blocks for weak interaction, building blocks of what? Building blocks of my interaction term in the Lagrange. Okay. Has to have the form of some neutrino, say L, this is L and not E, then some stuff, and then the corresponding lepton which has the same lepton number, family lepton number, times or, so building blocks are this or something which is opposite, okay, L bar mu L, because it conserves lepton number. Okay, is this clear? I've sort of moved to a situation where I know what I must use to build this. So there will be E here and E here in the muon case, or mu here and mu here.
What will be
This
in
one.
between?
What the target?
No, so I'm saying this is one current. See the matrix element, okay, so matrix element, if you look say at QED, has the form of some charges which give you the strength of the interaction times a current J mu and some other current J mu, and then say for the photon there is a propagator which goes as Q square. This is the form that you know from QED. So this is one current now, except that I don't know that it is like, U bar, gamma mu, something like that. I don't know what is here. Okay. So I'm trying to build that, but I know it has to be some current type of object. Or at least I'm assuming that and proceeding. In the end, you will test against experiment and see if the matrix element square that you calculate gives you the right decay width or not, which you see in the lab. Okay, so then you can ask, well, how do you know what the coupling is? When you calculate the matrix element, you have to put in some numbers like E for the electromagnetic part. Where what you do is that you measure say the muon decay rate, and then you leave the coupling unknown, and measuring the rate you say, okay, this must be the coupling, okay, because the other things you know. Then you go and check another decay. If the same coupling works there, then you have found what the coupling is. Otherwise there is something wrong. Is this clear? Because the couplings are not going to change from interaction to interaction, the same way that the QED coupling doesn't change from interaction. And that's not a totally accurate statement, because when we do the standard model you'll see it's more complicated. But in general, as a simple statement, this is true. So you see, does that answer your question? Okay. So, I'm actually looking for these things. So I am constrained by the fact that this is a Lorentz invariant. And matrix element is current times current. So it goes as current times current, where the current has this is one current. Okay. So, and it should lead to a Lorentz invariant object. Okay, because mod m square is going to give me a real number or a scalar.
This is an anti-electron bar. No, for the second is or L.
No, this bar actually represents the outgoing particle. Okay, because alright, so let's see. Here is a here is a say E minus. Okay. Then there is, as we indicated, there is a gauge goes on that actually is charged. So it's capable of taking away the charge. There's a W plus and a W minus, so I can use both. Okay, so this E minus charge is going away here, so charge is conserved, electric charge is conserved at this vertex. And then I have a new E, because lepton number must be conserved. So this is a particle. It's an outgoing particle. So in that case, this will become nu E bar and E, incoming electron. Okay, so there's a U spinner and V, this bar spinner and so on. Is this clear? So this, for instance, is a U type of object with some stuff. Alright, so I have to build things with gamma matrices and two size Dirac spinors, right? So what are the possibilities? Which, when contracted, there is one current, when I contract it with another current, I need a Lorentz invariant quantity. So I can list things which will allow me, combinations of which will give me a matrix element that's Lorentz invariant. So when I do that, there are possibilities. So these are not necessarily the same Dirac particle. So I have psi 1 bar, psi 2. Okay, and psi 1 bar, gamma 5, psi 2 as another possibility. So there's nothing in between. These dots are just one, or for instance, they are gamma 5. Okay, or it could be psi 1 bar, gamma mu, psi 2. This is your familiar QED type of vertex. Or it could be psi 1 bar, gamma mu, gamma phi, psi 2. Or finally, you could have a complicated thing which we are not going to use in this course. There's a tensorial vertex. So there's gamma mu, gamma nu, psi 2. This is also possible. With a spin 2 gauge boson, you have a vertex like this. If you want Lorentz invariant matrix element. So these have names. Okay. But more importantly, they have different parity properties, and I'll come to why I'm looking at parity and not other things. So they have different properties under space inversion, these objects. Okay. So this space inversion property will get reflected in the interaction vertex. Okay, that's why it's important. So let me write down the parity properties. So parity, as you know, is basically x going to minus x. Right? The space parts change sign. It's a reflection in ordinary space. It's a reflection of a vector around the origin. Okay? So it's not a gradual rotation. It's x going to minus x. It's what is called a discrete symmetry. Okay. Alright, so this is what this is, and I'll give you a homework that allows you to check that something like this is even under parity. Okay, so it stays the same. This plus 1 means that. Something like this is odd under parity.
So even under parity means it doesn't change under parity also.
Yes.
It is Lorentz scalar.
Huh?
That is Lorentz scalar. That's
This object is a Lorentz scalar, yes. That's the reason why it is even under parity. Now you see, it also is just a one component object. Because a scalar like temperature or mass or other scalars has a single value. Okay. Whereas something like this has 4 components. So there's also this number of components are changing depending on what we have here. Okay. Alright, so for something like this, the transformation under parity is -1 mu. I'll explain what this means. And for something like this, it is -1 -1 mu. And for something like this, it is -1 mu times -1 mu. Okay. So this is called, as you said, a scalar. This is called a pseudo scalar. This is a vector. This is an axial vector or pseudo vector. And this is a tensor. We are considering the forms of this interaction that we are trying to understand can take here. What can I put here? And arrange things. I can put combinations of things and arrange things so that in the end this J mu gives me a Lorentz invariant quantity. Okay? And I don't know the answer offhand. I have to try things out, follow conservation laws to build the vertex, and then check against experiment. That's the idea. Okay. So I haven't explained what this is. -1 mu is equal to 0, (1) if mu equal to 0, and is equal to -1 if mu equal to 1, 2 or 3. So for the space components it's -1, and for the 0th component it's +1. It's defined like that. Okay. So this is a vector. Okay, so why do we call it a vector? Because under parity the time component will not change, but the 3 space components will get a minus sign. That's why it's called a vector. Okay, and the same for these. I'll come to these things in a moment. But having talked about parity, I want to give you a little more idea of what parity is, because it's very important in the weak interactions. Again, discrete symmetries. If something conserves parity, as we will see, QED conserves parity, QCD conserves parity. If something conserves parity, so it's a conserved quantum number but not necessarily associated with a gauge symmetry. only selected conserved quantum numbers like electric charge or like color for the strong interaction are associated with gauge or local symmetries. Okay. Alright, so I want to say a little bit more about parity. So we'll come back to the calculation of muon decay later. This is a small digression to give you an idea of what parity is. Okay, so see, the basic things we work with are these kinds of objects. Okay, so let me assume that there's a parity operator. When it acts on this, since I know what parity is supposed to do, I will get psi minus x t when it operates on this.
It is only space inversion.
Space inversion only, yes. So P of must give me the same object, because if I operate twice, I'll get back this. So also P of dagger P of must be equal to 1. It's a unitary operator in all quantum, like all other quantum mechanical operators. So this tells me that P dagger of is the same as P of. Okay. So if the eigenvalue is represented by P, so P of is the operator, and let me represent its eigenvalue by P. So P square is equal to 1. Alright. So that means P is equal to plus minus 1. And this is the eigenvalue, and this is the operator. Right? So if, I probably should write that down, if a certain interaction conserves parity, then each interaction will commute with PO. Is that clear? Okay. Just your usual conservation statement. So if a particular psi is an eigenstate of H8, then that will also be an eigenstate of P, which means it will have eigenvalues plus minus under the operation P. Okay, plus minus 1. Okay. So look at QED. Why am I doing that while talking about weak interactions? I'm looking at it because QED conserves weak interaction. We want to understand what exactly conservation, I mean QED conserves parity, and we want to understand what exactly that means at the Lagrangian level. Okay. So look at QED. Let me look at something like E minus going via photon to QQ. Okay. Quarks also carry electromagnetic charge, so there is an electromagnetic interaction between electrons and quarks. So my M for this will have the form some quark charge times some E and divided by Q square, where Q square is the photon momentum, okay, times two currents. There's a J E mu current and there's a J Q mu current. Is this clear? This is the quark current, this is the electron current. Q square is the propagator. This is how the matrix element is built. And this current, J E mu, is basically, so let me call this like we usually do, PA, PB, K1, K2. So J mu is going to be U bar K1 gamma mu U PE, right? And my J Q mu is going to be U bar K2 gamma mu U PB. Right? Okay. Now I try to give a homework where you show that the P operator can be built or constructed by using gamma 0. I'm not showing that now, it will be part of the homework so you understand that. But the P operator has to be represented by something that acts on spinors. So a good choice is gamma 0. You will show that in the homework. Okay, so I am assuming that there is the P operator, and then so U under the operation P, this U spinor will be gamma 0, okay, and a U bar spinor will be U bar gamma 0. Okay, is this clear? Because U bar corresponds to, if I want to operate on it with P, I will first put P U here, then I'll have a dagger, then I'll have a gamma 0. Okay, so I'll get basically U bar gamma 0. Okay, so using this, I try to see what happens to these currents under parity. So J E mu under parity will become U bar gamma 0 gamma 0. Okay, J E 0. I'm looking because the properties of the zeroth and space components are different under parity. First, looking at the zeroth component of the electron current. Okay. So there I will have 3 gamma zeros and a U. This is the current. Okay, so there's 1 gamma 0 from here, 1 gamma 0 here, and 1 gamma 0 here. Is this clear? So this of course gives me the same current back because it's U bar, these two are 1 and this is just, so I get under parity gives me the same thing. That's not the same for the kth component. So J E K under parity gives me U bar gamma 0 gamma K gamma 0 U and that is minus of, when I change these from here to here, I get a minus sign. So I get minus of U bar gamma K U. Okay. Is this clear? Because the space and this anti-coupled. So this is minus J E K under parity. So you see this, at least in this case, this operator choice is giving me the results I want. Alright, so what about the full current? So J E mu is J E 0 minus J E K. Okay. So the full current no, that's not correct. I want to look at J E mu times J Q mu under parity. Under parity, this current will have the same transformations as this. So I will get under parity. This product will become J E 0 J Q 0 minus J E K J Q K. Okay, this being careless. Okay, and these go minus minus gives me plus, gives me the same product back. Okay, so what is the is this clear? This conclusion is clear that you get the same for the contract. The matrix element is a contraction of these two. It is this object that has to conserve or not conserve parity. So this current has to basically conserve, this product has to conserve, and it does, as you can see, because these will go to minus minus, but there's two of them. Okay. And these will remain the same under parity. Alright. So the parity transformed object is the same. So what is the conclusion? The conclusion is that QED vertices conserve parity. In other words, it doesn't matter whether these are charges or whether they are the color charges. And QCD is also a vector interaction, has this gamma mu and nothing else. Okay. So QED and QCD, because of this reason, conserve parity. Is that clear? Okay. And so does QCD, because that interaction vertex is exactly like this, but the couplings are strong and there will be quarks here or so on, and there will be a gluon here instead of a photon. Okay, but it's the vertex that decides the property under parity. And the conclusion you come to by looking at this current structure is that QED conserves and QCD conserves this. Now we'll take this up next time, because we'll find that weak interaction does not conserve parity. So then you have to go and construct from those alternatives something that will give you parity non-conservation at the vertex. So that's the idea. Okay, Friday.